Okay, kids, let's start bio. Even though I know you're going to be confused because you're going to be like, wait, this is chemistry, but it's the chemistry of life. And biology is life. Honestly, though, I'm mostly going to use this as kind of a way to gauge how much you learned in grade 7, 8, 9 from teacher Vanessa. A lot of this should be review. You should understand most of this already. So we're going to kind of like zip through this. Okay. So today's topic is the composition of matter. Now, Earth supports an enormous variety of organisms, two of which are the chicken and the turtle. The structure and function of all living things are governed by the laws of chemistry, which is why we have to make sure that we understand the basic principles of chemistry so that we have a better understanding of living things and how they function. Now, everything in the universe is made of matter. What is matter? Anything that has mass and takes up space. So there's two properties for matter. By the way, all of the vocabulary is going to be in red. So that helps you understand what words you have to know and what you don't, I guess. So anything that has mass and takes up space. Mass is the measurement of the amount of matter in an object or the quantity of matter an object has. Okay, so matter has two requirements. Mass and take up space is another word for well, three words. Oh, is that behind my picture? Volume. Mass and volume. 1, 2. That's what matter is. Matter has mass, matter has volume. Elements. So everything's made of matter, and elements are pure substances that cannot be broken down chemically into simpler kinds of matter. All of the elements are arranged in a chart called the periodic table, which you see here. More than 90% of the mass of living things is composed of just 4 elements, which is what we kind of focus on in biology. Oxygen, carbon is the big one, hydrogen, and finally nitrogen. Now on the periodic table, each element has a different chemical symbol that consists of 1 or 2 letters. Now the 1 or 2 letters is going to represent either the name of the element in English or perhaps from its Latin root. So for example, Na is sodium, and sodium. And you might think, well, what does Na have to do with sodium? It comes from the Latin for sodium, which is natrum. So there's your Na. Same thing with iron. Iron is Fe. Where does Fe come from? The Latin for iron, which is ferrum. Copper. Copper is Cu. Latin cuprum. So if you see an elemental symbol on the periodic table, which doesn't seem to come from its elemental name, it comes from the Latin for the elemental name. Okay, this is an atom. An atom is the simplest particle of an element that has the properties of that element. An atom has 2 main parts. You have the nucleus in the center that makes up most of the mass of an atom, and then surrounding the nucleus are electrons. There are 2 kinds of particles in the nucleus. You have a proton, which has a positive charge, and a neutron, which has a neutral or 0 charge. I should also mention, because I don't think I did. I didn't. Electrons have a negative charge. Now, elements are defined by their atomic and mass numbers, which you find both on the periodic table. So this is what you would see on the periodic table, and the atomic number is the number of protons in an atom. This is the defining characteristic or the unique characteristic of each element. each element is defined by how many protons are in the nucleus. So if an atom has 8 protons, it is an atom of oxygen, not any other element. Atomic mass or mass number, however, is going to be in decimal form because it's going to represent an average of the isotopes, which I don't know if I talk about here or in chemistry, but I will talk about isotopes eventually. But the reason why it's a decimal is because it's an average. So mass number or atomic mass is the number of protons plus the number of neutrons. So if I ask you how many protons, neutrons, and electrons are in an atom of oxygen, sorry about that noise, that's my vacuum cleaner running downstairs. We have an atomic number of 8. So protons, I'll just use a P with a plus to represent protons. That's 8. Now, mass number minus atomic number equals the number of neutrons. Because it's a decimal, I'm going to round it up. So that's 16. 16 minus 8 is 8. And I put a 0 next to the N to indicate a neutral charge. Now, what about electrons? How do I know how many electrons there are? Well, in an atom is electrically neutral. So that means that if an atom doesn't have a charge overall, but it's made of little pieces that have a positive and negative charge, in order to be neutral overall, it has to have an equal amount of positive and negative charges. So if it has 8 protons, it must have 8 electrons as well. And I will give you a worksheet to practice calculating this. But moving on. Electrons. Electrons, I just talked about that. The number of protons and electrons have to be equal. Now, what is this kind of weird psychedelic looking stuff? I mentioned that electrons are around the nucleus, but they're actually in what we call orbitals. Orbitals are these weird shapes you see. These are probable locations of an electron. I say probable because there's no way to know for certain. There's no way to pinpoint exactly where electrons are. But we can point to kind of an area where we say electrons probably exist in this area. Now, they exist in levels. So you see, when we're going to go into this in detail in chemistry, but you see this is 1, all of these are 2, all of these are 3. So these are the levels I'm talking about, and you'll learn way more than you ever wanted to know about orbitals in chemistry, but I'll save that for later. The important thing to understand is that electrons, as they move away from the nucleus, their energy becomes higher and higher. And these orbitals correspond to specific energy levels. Each energy level corresponds to a group of orbitals that can hold a certain number of electrons. So as you move away from the nucleus, you're going to add more orbitals, more possible locations where electrons are, and they're going to have more and more electrons. So for example, level 1 can hold only 2 electrons. So no matter what the element is, here we have oxygen, here we have magnesium. The first level can hold only 2 electrons. So all atoms, except for hydrogen, which has only 1 electron, they start from level 1 and they fill level 1 first, and then they go to level 2. Level 2 can hold 8, level 3 can hold 8, and then we go up from there. So in the second level, there's a total of 4 orbitals, I should mention, although like I said, I'm going to talk about it more in chemistry later. Each orbital holds a maximum of 2 electrons. So the number of electrons total for every energy level depends on how many orbitals there are. In energy level 1, there's only 1 orbital, so there's only 2. In energy level 2, there are 4 orbitals, 2 electrons each, for a total of 8. Next are compounds. These are pure substances that are made of atoms of 2 or more elements. The proportion of each type of atom in a compound is fixed. For example, H2O has 2 parts hydrogen, 1 part oxygen, always and forever. Excuse me a sec. The physical and chemical properties of a compound are different from the properties of the elements that it's made of. For example, going back to water, water is made of hydrogen and oxygen. They are each colorless gases, but water is a clear, odorless liquid. Very different properties. Now, just looking at the properties of hydrogen, 99% of all of the matter in the universe is hydrogen. It's what makes up about 95% of the mass of our sun, which you can see here. And it's also a source of a hugely damaging weapon. And when you pass electricity through it, it kind of glows this purpley color. I'm going to turn the volume down, but this is the Hindenburg. It was a passenger, they carried passengers, and you can see here that it caught fire in a terrible, terrible accident. I don't remember what year it was. It was the early 1900s. So why did this happen? Because back in the early 1900s, people, planes weren't a thing. Like airplanes were still kind of in the early stages of development. So they thought, okay, well, balloons float. So if we make a big enough balloon, then we can put a little carriage on the bottom of that balloon, and it can float people and go different places. It had like a fan at the back. Sorry, my throat's really dry. Anyway, when the scientists were trying to figure out what gas do we fill the balloon with, they thought, well, hydrogen is the lightest element, so that would surely make the balloon float the most. What they didn't realize or didn't think about is hydrogen is highly, highly flammable, which you obviously see from this video. So I think it hit an electrical line or a spark from something, and the whole thing, as you see, got engulfed in flames. So that's properties of hydrogen. The other element that makes up water is oxygen, which is released by plants. Obviously, we need it to breathe. When you pass electricity through oxygen, it's really similar to hydrogen. It's kind of this purpley color. And it's also flammable. It's what do you call that? The space shuttles, it's what they use for fuel, like literally. They use liquid oxygen for fuel. And that takes them into space. Water, obviously, it's needed for life. We drink it. We got oceans of it. In the bottom picture, that's a hydroelectric dam. We produce lots of electricity with it, but it can also be very, very devastating as well. Nope, 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 run away. So how elements combine and form compounds depends on the number and the arrangement of electrons in their orbitals. The atoms will reach chemical stability when orbitals in their highest energy level are filled with the maximum number of electrons that can hold them. This is the basis for chemical bonding, which we'll talk about later in chemistry. Now, some elements have atoms that already have the maximum number of electrons in their outermost orbital. These are called the noble gases. They are inert, which means they do not react. Most atoms are not in a stable natural state. What you see here, I believe, is sodium, pure sodium. It reacts very violently just with regular water. So atoms want to be stable, and so that's why they react. When atoms react, they form what are called chemical bonds. These are attractive forces that hold them together. There are two major types of chemical bonds. One is covalent bonds. This is when atoms share electrons. So remember when I said that, energy level number 1 can hold 2 electrons? Well, we have hydrogen here. Each hydrogen has, well, we did have hydrogen there. We have hydrogen, each hydrogen has 1 electron. So if two hydrogens each share 1 electron with each other, then they can both have 2. sharing is caring. When a covalent bond forms, we call that compound a molecule. So molecule, the word molecule specifically implies covalent bonding. So one molecule of a compound of water is H2O. One molecule of, that should say, this is wrong, sorry, element. I can't write properly. It's been so long since I've had to write anything. So you have a molecule of an element or a molecule of a compound. What distinguishes the two is whether or not you have all the same type of atom or you have different, or I should say element, whether you have the same kind of, whether you have the same type of atom or different types of atom. So a molecule of a compound has different types of atoms. Molecule of an element has the same type of atom. Now, one important thing is for diatomic molecules, I want you to remember these. All of these, basically it's hydrogen, nitrogen, oxygen, and then the halogens are group 17. These are diatomic, which means they come in pairs naturally. So you don't ever just see hydrogen, like one hydrogen atom, one nitrogen atom, or one oxygen atom. It always comes in pairs. Remember that. Okay, lastly is ionic bonds. This is the other major kind of bond. So an example of an ionic bond is when electrons are lost and gained. And the perfect example of this is sodium and chlorine. So sodium has one electron in its outer shell, which you can see there. Chlorine has 7 and it wants 8. Sodium wants to get rid of that electron. So when sodium gives an electron away to chlorine, it leaves sodium with a net positive charge because the number of protons doesn't change, it's still 11. But once it gives an electron away, it now only has 10 electrons. So 11 protons and 10 electrons gives you a charge of +1. This is now called an ion. An ion is an atom or a molecule that has a charge, whether it's positive or negative. So you can see from this diagram, sodium loses its outer electron, which is this one here. So it goes from having 3 levels down to 2. This is a sodium ion because it has a charge. Now, the same thing happens, but on the opposite side with chlorine. Chlorine has gained an electron, so it now has 1 more electron than protons, so it takes on a negative charge. And the last part of the formation of an ionic bond is that we have now formed 2 ions. We have a positive ion and a negative ion. And what do we know? What do we know about positive and negative? Is that they attract. Sorry about that. So because positive and negative attract, the sodium ion and the chloride ion are attracted and they form an ionic bond. And for sodium and chlorine, as an example, the resulting compound is sodium chloride or salt.